Hi everybody. Today we're going to be learning about covalent molecules. But before we get to covalent molecules, we need to review a couple things from the periodic table and from one worksheet that we did just a little bit ago. So let me start by reviewing that the dividing line between the left and the right side of the periodic table is the metalloid stair-step line. And we have metals on the left side of the stair-step line, and we have nonmetals to the right of the stair-step line. So we've got seven metalloids right here that we highlighted in blue. And what I'd like us to do is to use that same blue highlighter and highlight the metalloids on this unique periodic table right here. I'm just going to put a slash through them real quickly here. All right, so there's the 7 metalloids, and remember that separates the metals from over here from the nonmetals, which are over here. The next thing I want to review is that unlike covalent molecules, we already learned that ionic compounds have a cation, which is typically a metal, and an anion, which is typically a nonmetal. So ionic compounds typically have metals and nonmetals, and so they come from distant sides of the periodic table. That's in contrast to covalent molecules, which bond 2 or more nonmetals together. So we're going to put this note up here. So covalent molecules have 2 or more nonmetals. In order to emphasize that, I'm going to use my orange highlighter. I'm going to highlight nonmetals in orange, and then I'm just quickly going to go through and mark all of these nonmetals that are on the right side of the periodic table. Now occasionally you'll see some of these group 8 noble gases in covalent molecules as well. Typically we know that because they have a stable octet of 8 valence electrons already, they don't want to form bonds, but occasionally some of them do form bonds with other nonmetals. One last nonmetal that we need to highlight, and it's hydrogen. It's the only element that seems out of place on the periodic table. So it is a nonmetal, even though it's on the far left-hand side of the periodic table. So again, you can easily spot a covalent molecule if it bonds any of these orange nonmetals together. All right, now what we're going to do is to get into the notes. So the first question asks us to describe a covalent bond. And it says covalent bonds involve 2 bonded valence electrons. Okay, those bonded valence electrons, they're pretty much right in the middle in between the 2 bonded atoms, although they might be slightly off-center for reasons that we're going to talk about in the context of electronegativity coming up. Concerning electronegativity, now this year, 2020, because it's a unique year, I've done things a little bit out of order so that we can be really successful with the biggest ideas. But right now, in order for us to understand that, we have to go back, understand this, we have to go back and understand electronegativity a little bit. So electronegativity is defined as follows. It is strength of attraction for bonded valence electrons. Electronegativity is defined as strength of attraction for bonded valence electrons. All right, let's get a better understanding of what this means. Now, if we have an ionic bond, which includes a metal and a nonmetal, what we can do is we can use this unique periodic table, and we take this number right here, 0.93, which is the electronegativity, the measure of strength of attraction for bonded valence electrons, and we look at what it's bonded to. Let's say that we're talking about table salt, which is sodium chloride. The chlorine has an electronegativity of 3.16, and the sodium has an electronegativity of 0.93. Because there's such a big difference in electronegativity, the electrons in the bond are going to go much closer to chlorine because chlorine has a higher strength of attraction for those bonded valence electrons. So I would put something like this, an example of an ionic bond equals NaCl. And if I put a little space in between them, I could put my 2 interacting bonded valence electrons way closer to chlorine because chlorine is much stronger. It's got an electronegativity of 3.16, whereas sodium has an electronegativity of 0.93. This is the case of an ionic bond, but this is about covalent molecules and covalent bonds. So let's take a look at an example like nitrogen bonded to oxygen. See how we've got two or more nonmetals right here, so we know it's going to be some sort of covalent bond. Let's say that we're talking about the example of CO, carbon monoxide. Again, if I put a space between the C and the O, oxygen is a little bit stronger at 3.44 than is carbon at 2.55. So those electrons are going to be a tiny bit closer to oxygen, but they're still going to be pretty much right in the middle. So again, let's go back to this statement right up here. In covalent molecules, the bonded electrons are pretty much right in the middle of the two atoms, but they might be slightly off-center also, as we've shown in this case right down here. So what we've learned that we can do is we can take the electronegativity values from this unique periodic table, we take the bigger one, subtract the smaller one from it, and the difference tells us the degree to which the electrons are offset. Here there's a really big difference, so they're closer to the stronger one. Here there's not so big of a difference, so they're kind of ish right in the middle. We're going to come back to that idea in just a second. All right, next note. Covalent bonds are classified by taking the difference between the bonded atoms. Okay, so taking the difference between the bonded atoms. If the difference is less than 0.7, then the bond is classified as nonpolar covalent. If the difference is between 0.7 and 1.7, then the bond is classified as polar covalent. And finally, if the difference is bigger than 1.7, then the bond is classified as ionic. And remember, an ionic bond is not a covalent bond. Now that's a whole lot right there, so let's summarize this. The first thing that we need to understand is this word difference. So the question is, what does the word difference mean mathematically? Difference means you subtract. So what you can do is you can take the difference between the bonded atoms, which we're going to do in a second, and you're going to plot it on a scale that we're going to recreate right down here in the lower left-hand corner. So in this scale, I'm going to put 0, 0.7, 1.7, and then on the far right-hand side, I like to put big number. And these numbers that we've plotted here represent the difference between the two bonded atoms. Okay, so it's not the numbers from the periodic table, it's the difference between, say, this number minus this number. So let's give this a try. First of all, see how if it's less than 0.7, we call that a non-polar covalent bond. If it's between 0.7 and 1.7, it's a polar covalent bond. And if the difference is bigger than 1.7, it's ionic. All right, let's give this a try. When I type in the electronegativity values for chlorine and sodium, it's 3.16 minus 0.93. That equals a difference of 2.23. And see how a difference of 2.23 puts it squarely in this ionic region. Well, we already know that sodium chloride is ionic because it mixes a metal with a nonmetal. Let's take a look at another example. We took a look at oxygen and carbon. If we take 3.44, subtract 2.55, comes out to a difference of 0.89. 0.89 puts it right about here, and so this would be classified as a polar covalent bond. Okay, and again, in a polar covalent bond, the electrons are ever so slightly offset, closer to the one with the higher electronegativity, because you should think of this number right here as if oxygen's been going to the gym a lot, and carbon hasn't been going to the gym nearly as much as oxygen has, so oxygen is stronger. All right, so that's how you take the difference in electronegativity values and you plot it on this scale to classify the bond type. Okay, you can see I moved the paper down. Next guiding question, what type of elements are held together with covalent bonds? Well, that was the purpose of us using the orange highlighter up here. Covalent bonds hold together, I'm going to be real specific here, they hold together neutral nonmetals. which are found to the right of the metalloid stair-step line, again, with the exception of hydrogen. Now, I've used this word neutral right here because you might remember that the nonmetals, when they form anions, when they turn into anions, they like to take negative charges. Well, think about it. If negatively charged nitride ion were to try to attach to oxide ion, which is also negatively charged, those two like charges, they're both negatives, they would repel from one another and they wouldn't be able to bond together. So in covalent molecules, it's not that we have charged particles bonded together. That's the case of ionic compounds. Rather, in covalent molecules, we have neutral nonmetals bonding together, or to the right of the metalloid stair-step line. Okay, now we get to writing names and formulas. The good news is that it's much more difficult to write names and formulas for ionic compounds than for covalent molecules. What we're going to do is, once you spot that you have only nonmetals in your substance that you're looking at, like for example phosphorus and chlorine, see how phosphorus and chlorine are both orange nonmetals. Once you spot that it's a covalent molecule, we're going to use a prefix naming system to report the number and type of each element in the compound. We're going to write down the names for these different prefixes right over here. All right, 1 is the prefix mono, 2 is the prefix di, 3 is the prefix tri, 4 is the prefix tetra. I know it might make sense to use like quadra or something like that for quadrilateral, but we use tetra to mean 4 of something. Now from this point on, I think you'll hear that most of these names have to do with geometric shapes. So 5 is penta, 6 is hexa, 7 is hepta, H-E-P-T-A. Again, I know you might have heard of septa before, but we use hepta to refer to 7. 8 is octa, like an octagon, a stop sign. 9 is nona. And 10 is deca, D-E-C-A. All right, so we're going to use a prefix naming system to report the number and type of each element in the covalent molecule. If you take a look right here, the first example is phosphorus pentachloride. So the formula for phosphorus pentachloride is PCl5, because penta refers to 5 chlorines. The next is sulfur hexafluoride. This is going to be SF6, because we've got the prefix hexa attached to fluoride, so there's 6 fluorines. The next is xenon pentachloride. This is XeCl5. One thing that you might notice here becomes important. See how there was no prefix before the first one? If there's no prefix before the first one, it means there's only one of that first one. And that's really the only oddball rule with covalent molecules. We'll touch on this again in just a minute. All right, now we can go from formulas to names. N2O5 would be, the 2 is dinitrogen. And the 5 is attached to oxygens, so the oxygen, so it's pentoxide. CO2, so this is going to be carbon dioxide. We're all breathing this out right now. And the last one is going to be CO. There's only one of the second one. This is where we use that prefix mono. So this is carbon monoxide. Okay. So the note is that the prefix mono is never used with the first element in the formula, only with the second. So see how there's only one carbon here? We don't say monocarbon dioxide. We only use the prefix mono if there's one of the second. So this would be carbon monoxide. Okay, I'm going to put a star next to that last thing. It really is the only unusual rule when you're using this prefix naming system to report the number and type of each element in a covalent molecule. All right, thanks a lot, guys. My suggestion is that you now move on and do 3.1 practice, formulas 5. Thanks a lot. Have a good day.